So exact equations. So this is the part where you start learning how to actually solve different types of situational differential equations. Okay, but before we get there, there's a little bit of background when it comes to it of implicit differentiation. Okay, so remember, implicit means we have two variables, not just one, like y prime. It's now x y prime, right? It's not just in terms of just one individual variable. Okay, so remember back in multivariable calculus, this type of stuff was called level curves, or things like this. Where in multivariable, you went to the gradients, and then the curves itself. But the same process here, but what I'm trying to get to is the function itself. So the function is in terms of x and y equals some constant c. Okay. So for example, a simple example would be like that, right? It's x, y, and then just some constant. Okay. So in the general term, we have this situation. Now, the cool thing is if I take the derivative with respect to x, right, and we're doing implicit because it's in terms of x and y, just like I would take the derivative with respect to here, it's a product rule, right? So this becomes a product rule, which is just the derivative with respect to x and then this dy dx part. Okay? So this is supposed to be a d there, dx dy. And this is nice because the derivative constant is 0. And we already talked about how to solve for this type of situations. We did that last time. So in retrospect, if I do the exact same process over and over again, or look at what this actually represents, this is something, again, we talked about in multivariable, something called the total differential of f. It looks like that. Or the partial derivative with respect to x, where this is the derivative with respect to x on f, derivative with respect to f of y. So it's the partial derivatives, or add them together gives you the total differentiable, which is a different topic in multivariable. But we're going to do these two things to actually solve a differential equation. But we're going to slightly different format. So we're going to say a differential form of m with respect to x and y dx plus n with respect to x, y, dy is to be exact in rectangular R if for some function f this is true. So if I take the derivative with respect to the partial derivative with respect to x of this function f, I get exactly this. And if I take the partial derivative with respect to y of f, I get exactly the n value there. So in these situations, we're going to be dealing with, like, for example, things like that, where we have dx into it and dy. So it's a bit off-putting. It's not the normal implicit, it's not the normal differentiable equation we've been using before. Okay. Now, if this happens, so in other words, if this is true, that is the total differentiable f gives this, which is exactly what we had to begin with. Okay. Now, if this whole process is an exact differential form, then the equation, looking like this, is called the exact solution. Okay. Now again, the whole point is to solve for these kind of situations. Okay. Now this part we're just going to be, defining them itself to begin with. Then we'll learn eventually how to actually solve for them with a little twist. Okay. So once we get there, first we're going to figure out is, okay, first given this situation, we want it to look like this, where such that I need to find f, and when I take the derivative, it gives me that. When I take the derivative, it gives me this. In other words, these are the derivatives of the original f function. Now this is where it comes into play. Suppose the first partial derivatives of m and n are continuous. Okay? So meaning I take the derivative with respect to x and y individually, or the partial of it. Then this one is an exact solution. So this equation is exact solution if this is compatible. So in other words, before we even start solving for this type of situation, we first want to show or prove that this is actually true. Because if this is not true, then we actually cannot have an exact solution. That's the best part of the if and only if. Okay. So that's the key condition we're going to deal with first, and then we'll go backwards to see how we're actually going to solve itself. Okay. So let's actually use, how do we use this theorem? Okay. So the theorem is applied pretty straightforward. Is, for example, does the compatibility condition hold for the differential equation looking like this? Okay. So first thing all we do is just identify what we have so far. So m, the function m will always be next to the dx, and the n will always be next to the dy. So we label that. So m of xy is going to equal to 2xy squared plus 1, and then n is equal to 2x squared y. So all we want to show is, does this hold? Okay. So if this holds, therefore there is an exact solution to this. Okay, and that's the best part. If that doesn't hold, we can just say automatically a no, right? So that's our first condition we have to show anyways. Okay, so all we're going to do is follow this format. So I'm going to take the partial derivative with respect to y in this case. So take the derivative with respect to y and take the derivative with respect to x here. All right, so again, take the respect to y means x is a constant. So this is going to be 4xy, and the 1 just goes away. Take the respect to x, and look at that. So the condition actually holds. So if we want to actually solve for this, we can actually do that. But for now, it was enough just to show that it's compatible. Okay. So now let's see how this actually works out. How do we actually solve for this type of situation? So now we actually want to solve the exact solutions. Okay. All right, so first thing we're going to do is label everything we have. So m of xy is equal to 2xy minus secant squared x, and n of xy is equal to 2x plus 2y. So before we do anything, we want to show, is it compatible? Okay, so meaning take the derivative with respect to y, take the derivative with respect to x, and see does it actually work out. So let's see. So if I take this with respect to x, respect to y, that's nice. That goes away because it's a constant. We just get 2x. Okay. So now we take the derivative with respect to x. So that goes away, and we just also get 2x. So it works. So we will get an exact solution because of this now, which is great. Meaning we're not going to do all this work for absolutely nothing. All right, so here comes where the actual math comes into play. So let's go back a little bit. So we just showed that this is true. Okay. All right, so remember, these two are the derivative, the derivative of the original f function. My goal is to find the original f function that made this work, right? In other words, back up to here. Okay. So in order to do so, this is df, right? So the derivative. So that means to cancel out the derivative, we have to take the integral of both sides with respect to individual x and y. Okay. And that's exactly what the goal is here. Is just that's the plate work. So the first thing going backwards is now take the integral of both the m and the n with respect to x and y. So step one, we're going to take the integral of m Now, we have a bit of a problem. Okay, so remember, we want the original f value itself, which means because we're taking the derivative, or the partial derivative with respect to x, this is the partial derivative with respect to x, anything that has y, specifically just y in it, goes away. For example, if it was like plus y, if I take derivative of that, that goes away. So what I'm going to do is, I'm going to be plus g of y, where this only function is in terms of y. Okay. So now if I just take the integral old-fashioned way, again, with respect to x, this ends up being x squared y, and the integral of secant squared is going to be tangent x, and again this plus g of y. Okay. So this is going to be our f function. But again, that's only the partial. Okay. So that means I also have to do the integral with respect to n over here. So the integral of n, this time with respect to y. In the same process, I'm going to put plus now g of x, because there could be a function that's only in terms of x, which goes away when I take this derivative. Okay, so this ends up being x squared y plus y squared, again plus this g of x. All right, so now notice they have this in common, which is great. Okay. So therefore I know that in my f function we have x squared y, because they both have that individual term in common. Okay. Now I just put everything else that they don't have in common. So minus tan of x plus y squared. Now, if you notice, right, this is only in terms of x, which is exactly that process there, right? That goes away when I take the derivative. And notice this was only in terms of y, which is right here. So it looks like they follow that same template. So it looks like that's exactly my f function to begin with. Now remember, we want to find a solution to this. We just found the f function. And originally, it was always looking like this, right, with equal some constant. So the final solution or final answer we want to go by is equal to, just make it c or some constant equal to all of this. So this is our solution. So now let's try a couple more. So same process. Take the derivative of each one individually. So taking the derivative with respect to y, that goes away. We get e to the x from here. And this is just gets x e to the x. Okay. Take the derivative with respect to x. Ooh, we got a product rule. So we get 1. So we get e to the x times 1 is just e to the x plus x e to the x. And 2 goes away, and there we go. Compatible. All right? And now we're just going to follow the exact same template as we did above. Okay? So first thing, take the integral of m with respect to x. And oops, I forgot my y's here. Okay. All right, so the first part's not too bad. It just gives you x, and this is itself. But this is the bad stuff here. Okay. So this part is an integration by parts, so I'm not going to go through the whole process, but real quick, let u equal x, y. That means du is just going to be y. Let dv equal e to the x, and then v equal e to the x. So according to integration by parts, this part is this times this. So plus minus integral of this minus this. And if you notice, that is exactly the same. And these actually cancel with one another after you just, same integration. So we just get this at the end. So on the other side, the integral is actually much easier to deal with. And especially since we're taking integral with respect to y. So we just add on a y to all of these. So again, just like last time, they have this in common, and they don't have that in common. So that's our respective g of y and g of x. So our general equation is going to be c equaling to what they have in common plus what they don't have in common. And there we go. So let's try one more. All right, so with respect to y, so goes away. Derivative of sine should be positive cosine. So here, it's respect to x, so this stays the same. So it'll just be 3 x squared cosine y, and they both work. So check. Right, so now we go into the integration process. It's the integral of m first. So 1 plus x to the third center y plus gy of x. Okay, same process over here. All right, so this gives me sine. All right, so they have that in common. This is a 3 there. And looks like just that, because this has nothing here, so plus x. And there we go. So that's called exact solutions when we have this type of situation here.